There you go. Yeah. So today we're going to do a graphics pipeline. We're going to get through it. We're going to work on it, and we're going to see how we can best get it to actually like work. Right. So we're going to go through all the stages, and we'll do stuff. So we're going to create the graphics pipeline after the image views in here. Cool. So here we go. Create graphics pipeline. Is it just pipeline? Yep, just pipeline. Cool. And obviously a new void function of create graphics pipeline. Why am I doing that? Cool. There we go. And now let's get to work on creating the actual graphics pipeline. Start with the shader modules. What is a shader modules? Unlike early APIs, shader code Vulkan has to be specified in a bytecode format as opposed to human readable syntax. Oh, okay, sure. So we have to compile our shaders before we actually run them. So it's called SPIR-V, and it's designed to be used with both Vulkan and OpenCL, so they're both Kronos APIs. It is a format that can be used to write graphics and compute shaders, but we'll focus on shaders used in Vulkan's graphics pipeline. Yeah, because we're doing the first triangle, right? So we figured out how to do SPIR-V. So the advantage of using a bytecode is that the compiler is written by GPU vendors to turn the shader code into native code are significantly less complex. Okay. So obviously, this is kind of like an intermediate representation. So kind of like how if you're compiling LLVM, you have your Rust or like your Zig, and then you compile it into LLVM intermediate representation. And from LLVM intermediate representation, what you do is you then feed that into LLVM, and then that will take you into your compiled assembly. So it's effectively just continuing to go through with the like stages of compilation. We're just kind of doing that here, right? Cool. So the past has shown that human readable syntax like GLSL, some GPU vendors were rather flexible with the interpretation of the standard. Okay. So if you happen to write non-trivial shaders with a GPU from one of the vendors, it might not work. With bytecode, it's avoided. Okay, that makes sense. That makes sense. So we're writing the bytecode, and so that's the unified contract for shaders. And then from there, we have, the two sides. Amazing. However, that does not mean that we need to write this bytecode by hand. Kronos has released their own vendor-independent compiler that compiles GLSL to SPIR-V. Ah, amazing. So the compiler is to verify your shader code is fully standard compliant and produces one SPIR-V binary that you can ship with your program. Okay. You can also include the compiler as a library to produce SPIR-V at runtime. Okay, so, but we're not doing that. Sure. Although we can use this compiler directly via GLSL lang validated exe, we'll be using GLSLC by Google instead. So GLSLC is that it uses the same parameter format as well-known compilers like GCC and Clang, and includes extra functionality like includes. Okay, so it's slightly better. Both of them are already included in Vulkan SDK, so you don't need to download. Okay, that makes sense. That's cool. So GLSL is a shading language with a C-style syntax. Programs written in it have main. GLSL is a lot like C looks like. Yeah, vector is vec, 3D is vec3. Okay, sure, that makes sense. A vec3 can be constructed with a vec3, vec2. Okay, sure. And so, as the previous chapter mentioned, we need to write a vertex shader and a fragment shader to get a triangle on the screen. So next two sections will cover the GLSL code of each of those, and after that, I'll show you how to produce two SPIR-V binaries and load them into the program. Okay, so we will write the vertex shader first. Okay, so the vertex shader processes each incoming vertex, and so it takes in attributes like world position, color, normal, and texture coordinates, and the output is the final position in clip coordinates, and the attributes that need to be passed on to the fragment shader, like color and texture coordinates. These values will then need to be interpolated over the fragments by the rasterizers to produce a smooth gradient. Okay, sure, makes sense. So first we have to start with the vertex shader. We operate on the vertex. So a clip coordinate is a four-dimensional vector from the vertex shader that is subsequently turned into a normalized device coordinate by dividing the whole vector by the last component. So it's just converting it from positions on the screen to position -1 to 1. Okay, that checks out. That does in fact check out. So you should already be familiar with these if you have dabbled in computer graphics before. If you have used OpenGL before, then you'll notice the sign of the Y coordinate is now flipped. Sure, the Z coordinate now uses the same range. It doesn't direct 3D from 0 to 1. Okay. So for first triangle, we won't be applying any transformations. We'll just specify the positions and as normalized coordinates to create the following shape. We have the triangle. So that's the first triangle we're going to be doing, right? So we're going to be using those three coordinates, and we're going to be building off of that. Okay. So we can directly output normalized device coordinates by outputting them as clip coordinates from the vertex shader with the last component set to 1. That way, the division to transform clip coordinates to normalized devices coordinates will not change anything. Okay, so we have normalized coordinates and we output them as clip coordinates from the vertex shader. Wait, what? we normalize them and clip coordinates with 1, so we just say don't change it. Okay, so normally these coordinates will be stored in a vector buffer, but we'll be creating it in Vulkan and filling it with data is not trivial. So we're going to postpone the creation of that until... Okay, we're going to simplify it, sure. So we're going to do something a little unorthodox, include the coordinates directly inside the vertex shader. The code looks like this. So what? Okay. And then I'll call it vertex.glsl because we're doing that. Hashtag version 450. Right, so I assume that's just a version. Vec2 positions, and there's 3 of them here. That's just, it's vec2 array, and then, yep, and it's not curly braces, it's these. Yep, okay, and vec2, it's a comma here, and it's 0.0 and minus 0.5. Yep. And then we go 0.5, 0.5. And minus 0.5, 0.5. Minus 0.5, 0.5. Cool. So there's our vec3 that we've made. So 3 vec2s that we've made. And obviously void main. And so gl underscore position equals vec4. So it's a 4D vector of positions of gl underscore vertex index. And obviously 0 and 1. So we're not doing any transformations. We're just saying keep it as is. You know, don't change that, right? That makes sense. So the GL index variable contains the index of the current vertex. Is usually an index into the vertex buffer, but in our case, it'll be an index into a hard-coded array of vertex data. The position of each vertex is accessed from the constant array in the shader and combined with dummies z and w to produce positioning clip coordinates. The built-in variable GL position function as the output. Okay, cool. It's GL capital P position, vertex index capital V vertex index. Okay, cool. Now we have the fragment shader. Nvim fragment.glsl. Cool. So, hashtag version 450. Layout location equals 0. Out vec4 out color. So that's our output, I assume. Void main, and so out color is equal to vec4 1.0 comma 0.0 comma 0.0 comma 1.0. Right, so we're just setting it to red. We're gonna make a red triangle, and there we go. So the main function is called for every fragment, just like the vertex shader. Main function is called for every vertex. Colors of 4 components are RGB alpha. Unlike GL position, there is no built-in variable to store. There is no built-in variable to output a color for a current fragment. You have to specify your own output variable for each frame buffer, where the layout location equals 0 modifier specifies the index. The color red is written that is linked to the first and only frame buffer at index 0. Per vertex colors. Making the entire triangle red is not interesting, and wouldn't something like this look nicer? Oh, it's a nice famous triangle. So we have to make a couple changes to both shaders to accomplish this. First, we need to specify distinct color for each of the 3 vertices. The vertex shader should now include an array with colors, just like it does for positions. Cool. So let's go back to vertex. And so I'll just write this. Cool. So vec3, I assume. Yep. Colors, and there's 3 of them, equals vec3 array. There we go. And it contains a vec3. And I assume it's, it's a 1.0, 0.0, 0.0, not a semicolon, comma. Paste those down. Remove that one. Not 2. There we go. And there is a very nice colors array. And so we need to pass these per vertex shader colors to fragment shader so we can output the interpolated values to the frame buffer. And output for color to the vertex shader and write it in the main function. Okay. I'll put it down here. Layout location equals 0. Out vec3 frag color, and then frag color equals colors of gl underscore vertex index. Cool. Next we did add a matching input to the fragment shader. Fragment.glsl. And this is layout location equals 0 with in vec3, and I'm gonna call this in color. I'm gonna move it up here. Cool. And so out color equals vec4 with it's frag color, not in color. Frag color, and here I will just have the fragment color. Let me double check. Yep, it's frag color. Cool. So now we have that, and so we have the shaders. And so compiling the shaders. Create a directory called shaders in the root directory of file. You can store the vertex shader file, shader.vert and shader.flag. Okay, hold on. Make the shaders. Move fragment.glsl to shaders slash shader.frag. Yep. Move vertex.glsl to shaders slash shader.vert. It's vert, right? Yep. Yep. The context of shader.vert. Vim shaders shader.vert is this. Yep, that checks out. Main is that. Yep, checks out. And then we have a vertex.vert. Sorry, not shader.frag. And it should be like 4 lines. Yeah, there we go. Cool. Create a compile dot. I will not be calling it a bat. I will be calling it a glslc. Yep, okay. I will be calling it a compile.sh because I'm on Linux, right? Hashtag / bin / bash. Obviously, it's sh will automatically do that, but yeah. glslc. Oh, we're gonna put that in the place. Oh, there we go. glslc. Yeah, okay. Shader.vert -o vert.spv for spur5. Yep. glslc. Then we have shader.frag -o frag.spv. There we go. And obviously I'm going to move compiler.sh into shaders. Cool. There we go. So could place the path. Yeah, it works. And begin platform specific. Cool. So they just tell us to read and output it. Yeah. Compiling shaders on the command line is one of the most straightforward options. And there we go. So loading a shader. So now that we have a way of producing spur5 shaders, it's time to load them to a program and plug them into a graphics pipeline at some point. First, we write a simple helper function to load the binary data from the files. Cool. So we have the main. We need to include fstream. Include fstream. There we go. Why do I have caps lock on? Hold on, there we go. So there's fstream, and so we just have to keep going down, and we have to load the shader, right? So, in essence, yeah. So just a helper function, I will put it above the defines. Nah, not above the defines. I'll put it right here below those. Cool. Static. So it's a static function. Well, it returns a static variable. It's a vector of chars, and where we read file, a const standard string. It's a reference to standard string called the file name. And in here, all we're going to do is standard iStream file, and the file we're going to be pointing it to is the file name is going to be a iOS 8. Oh, binary. It's just us telling the format it's going to be in. And so if not file dot is open. So if the file isn't open, it's a function, right? Yep. Throw standard runtime error, and it's going to be failed to open file. Sure. Failed to open file. Standard iStream file. Oh, it's there we go. Standard IF stream. Input file stream. There we go. And so read file will read all the bytes from it and return the bytes in a byte array managed by a vector. And so we'll start by opening it with two flags, ATE. So start reading at the end of the file. Oh, from the end to the start. And read the file as a binary file? Sure. And if the files, we can use read position to determine the size of the file and allocate a buffer. Ah, that makes sense. That makes sense. And so size t of file size. So because we're reading from the back to the front, we are looking at the file size just kind of as is. File size equals size t. We would change the thing. File dot tell g. Cool. And so standard vector char of buffer. That's the size of file size. And so yeah. So after that we can after that we go back to the beginning. Okay. File dot seek g 0. So we go to the 0th element, and then file dot read, and we read into a buffer. So buffer dot data and file size. So obviously buffer dot data is pointed to the buffer, and I assume we just we close the file. Yeah, we can just leave it out. Return buffer. There we go. And then in our graphics pipeline code, we will read the data. So hold on, it's all the way down here, up here somewhere. There we go. Auto vert shader code equals read file shaders slash vert.spv, and then we obviously have a fragment code, frag shader code, and that's going to be again read file of shaders slash frag.spv. There we go. And so now we have that. And so then from here, we create the shader modules. So before we can pass code to pipeline, we wrap it in a VK shader module object. Let's create a helper function, create shader modules to do that. So I'll just put it above the graphics pipeline creation. VK shader module. And this is going to be create shader module. Cool. And so it obviously takes in a const vector char pointer, which is going to be our code, the spur5 code. And so we'll take a buffer with the bytecode as a variable and create a VK shader module from it. Creating a shader module is simple. We only need to specify a pointer to a buffer with the bytecode and the length of it. Okay, this makes sense. This makes logical sense. And so this information is specified in a VK shader module create infrastructure. The only catch is that the size of the bytecode is specified in bytes, and the bytecode pointer is a uint32 type pointer instead of a char. Sure, so if we need to cast a pointer with a reinterpret cast as shown below. When you perform a cast like this, you also need to ensure the data satisfies the alignment of uint32. The data stored is standard vectors, where the default allocator already ensures it satisfies the worst case. Cool. So, we're back to create info. Amazing. VK shader module create info, and this is going to be a create info, and then create info dot type is going to be a VK structure type shader create info ext. Oh, shader module create info. Shader module create info. There we go. So that does exist. Create info dot code size is going to be equal to code dot size. Then create info dot p point to the code is, I assume that's going to be code dot data. Oh, the -77 equals. Whoops. Oh, we have to reinterpret cast. Okay. That's what they were talking about, that. Reinterpret cast, type uint32 type. And from there we go. Pointer, uint32 type pointer. Reinterpret cast from const char pointer to uint32 pointer, cast away qualifiers. That feels fine. Oh, const. There we go. We don't want to cast away const. Then the shader module can just be created with the normal stuff. So vk shader module, and that's going to be shader module. And if vk create shader module, our device is a very friendly device. VK create shader module create info is a reference to create info. Allocator is null pointer. Our p shader module is going to be the reference to our shader module. And if this is not a VK success, as opposed to a non-Vulkan success, right? Then we throw a standard runtime error of failed to create shader module. Amazing. And obviously we haven't returned the shader module. Yep. Return shader module. And semicolon. Cool. There we go. So we have our shader modules. I've lost that code, unfortunate. Let's keep scrolling. There we go. So we have our shader modules. And so in a graphics pipeline, we obviously use the shader modules. So vk shader module, and this is going to be a vertex shader module. And so that is we're going to create shader module of our vert shader code, and then obviously vk shader module of our frag shader module. So that we're going to create a shader module of a fragment code, frag shader code. Cool. So now we have shader modules. So shader stage creation. We'll use the shaders we need to assign them to specific pipeline stage through vk pipeline shader stage create info. Oh my god, another create info. I love create infos. Create infos solve the most problems. Of course. Dang, okay. Cool. So we'll start by filling in the structure for the vertex shader, again in the create graphics pipeline function. So vk pipeline shader stage. Okay. Sure. vk pipeline shader stage create info vert shader stage info. Cool. Vert shader stage info dot s type. Oh my god. Vert shader dot vert shader stage info dot s type is a vk structure type pipeline shader stage create info. Insanely long name, but sure. Vert shader stage info dot stage, and I assume this is just going to be no, VK shader stage vertex bit. VK shader stage vertex bit, so it's a vertex shader. Then vert shader, oh, vert stager stage info dot module, and that we just point to our vert shader stage info, and then the name is main. Vert dot name, point to name is, and it's just going to be main. There we go. Not stage info, just vert shader module. Vert stager module. There we go. And so the next two members specify echoes known as the so it's the entry point, so we go to main. So it's possible to combine multiple fragment shaders into a single shader and use different entry points to differentiate between behaviors. Okay, so if this is assume you have like a shader and you like combine them all into like one file, and there's just like shaders, and then that's all your vertexes, and then now you can just change which one you're going to. Makes sense. One more optional member P specialization info, which we won't be using, but worth discussing. It allows you to specify values for shader constants. So you can use a single shader module where its behavior can be configured at pipeline creation by specifying different values for the constants used in it. This is more efficient than configuring the shader using variables at render time, because the compiler can do optimizations like eliminating if statements that depend on the values. If you don't have any constants like that, then you can set the member to null pointer, which our struct initialization does automatically. Sure. So modifying the structure to suit the fragment shader is easy. We duplicate it and we just change it to fragment shader. Okay. Slash vert to. I should not be doing that because that feels way too over done, right? So frag instead of the vertex shader module, we're going to be using the fragment shader module. And instead of the vertex bit, we're going to use the fragment bit. And we're going to go into main. Fragment bit. Yep. And so we'll finish by defining an array that contains the two structs, which we'll use to refer to them in the actual pipeline creation step. Cool. So VK pipeline shader stage create info shader stages, and so we're just storing them in an array. And okay, and then we're gonna have a vert shader module and a frag shader, no, stage info, not module, vert shader stage info. Cool. And then we go on to the next step. And so next chapter we look at fixed function stages. So fixed functions. So the older graphics APIs provide a default state for most of the stages in the graphics pipeline. In Vulkan, you have the explicit about most pipeline states as it's baked into an immutable pipeline state object. In this chapter, we will fill in all the structures to configure these fixed function objects. Oh my god. Okay. Sure. Amazing. This makes a lot of sense. Cool. Dynamic states, vertex input assembly. Okay, it just keeps going and going and going. Okay. So this is just filling in default values and kind of going at that, which makes sense. So, dynamic state. We start with making some VK dynamic states. Standard vector. It's a vector of VK dynamic states. And we'll call it dynamic states. And so that's something like that. So it's a VK dynamic state viewport and scissor. VK dynamic state viewport and a VK dynamic state scissor. Cool. And so we have to have dynamic state create info. Sure, amazing. VK dynamic state create. Okay, hold on. The caps at the start is screwing me over a little bit there. What? VK pipeline dynamic state create info. Of course, our good friend. Oh, it's called dynamic state. Cool. So dynamic state dot s type is going to be equal to vk structure pipeline dynamic state create info. Yep. Pipeline dynamic state create info pipeline type. These names are actually insanely long. Like I don't know. Dynamic state dot dynamic state count is equal to static cast uint32 type onto dynamic states dot size. Then we have dynamic states dot, it's a pointer to the dynamic states, not dynamic state dot p dynamic state is dynamic states dot data. Cool. And so this will cause configuration of these values to be ignored, and you'll be able to and required to specify the date at drawing time, the data. This is also the most flexible setup, and it's very common for things like viewport and scissor state, which would result in a more complex setup when being baked into a pipeline state. Okay, so if you want to use those dynamically, we will use them in a dynamic manner, right? So this checks out. Vertex input. The VK pipeline vertex input state create info structure describes the format of the vertex data that will be passed to the vertex shader. It describes this in roughly two ways. The bindings, so the spacing between the data and whether the data is per vertex or per instance, so see instancing, or attribute description, so the type of attributes passed to the vertex shader, which binding to load them from, and at which offset. Okay, so we give it what data we are feeding in. Because we're hard-coding the vertex data directly into vertex shader, we'll fill this structure to specify that there is no vertex data to load for now. We'll get back to it in the vertex buffer chapter, which is immediately after. Cool. So VK pipeline vertex input state create info vertex input info, and now we fill it out. I don't want to fill out nulls, so we're just going to copy paste that in. This is just 0 null 0 null. And obviously it has optionals, but we will be doing the vertex buffers chapter as well. We'll probably be doing basically all of this, right? But yeah, cool. The p vertex binding descriptions and p vertex attribute descriptions members point to an array of structs that describe the aforementioned details for loading vertex data. Add this structure to create graphics pipeline function right after the shader stages array. Cool. So we just put it at the end. Input. Wait. After the shader stages array. Oh, okay, we put it there. Okay. Before dynamic states. Okay. Amazing. There we go. Input assembly. The VK pipeline input assembly state create info struct describes two things. What kind of geometry will be drawn from the vertices, and if primitive restart should be enabled. The format is specified in a topology member and can have values like this. So it can be a point list, a line strip, a triangle list, or a triangle strip. So second and third vertex of a triangle are used as the first two vertices of the next triangle. Okay, so we just specify points, and then we keep going. It's a list of... The triangle list is a list of triangles without reuse. The line strip is just... You just specify a bunch of points. And line list and point list. Okay. Normally the vertices are loaded from the vertex buffer by index in sequential order, but with an element buffer you can specify indices to use yourself. This allows you to perform optimizations like reusing vertices. If you set the primitive restart enable member to VK true, it's possible to break up lines and triangles into strip topology by using special index of max. So we intend to draw triangles throughout this tutorial, so we'll stick to the following data for the structure. And again, I am copy pasting this in because, yeah. import assembly, viewports and scissors. So viewport basically describes the region of the frame buffer that the output will be rendered to. This will almost always be 0, 0 to width height, and in this tutorial this will also be the case. Cool. I will put this at the bottom here. VK viewport is equal to viewport, then not equal to viewport. What am I doing? It's viewport. Viewport.x equals 0.0f. Viewport.y is 0f. And then viewport.width is equal to a float, because of course we deal with floats for graphics cards. Swap chain extent dot width, and then we have the height. Cool. Then we have viewport dot min depth is going to be 0.0f, and viewport dot max depth is going to be 1.0f. Cool. So now we have our viewport. So the size of the swap chain and its images may differ from the width and the height of the window. So the swap chain images will be used as frame buffer, so we should just stick to the size. Okay. The min depth and max depth specify a range of depth values to use for the frame buffer. These values must be between the 0 and 1 range, but min depth may be higher than max depth. If you aren't doing anything special, then you should stick to the standard values of 0 and 1. Okay. So while the viewport defines the transformations from the image to the frame buffer, the scissor rectangles define in which regions the pixels will actually be stored. Any pixels outside of the scissor rectangles will be discarded by the rasterizer, so they function like a filter rather than a transformation. So the difference is illustrated below. Note the left scissor rectangle is just one of the many possibilities that result in the image as long as it's larger than the viewport. Okay, so effectively, it only displays when you both have a viewport and the scissor rectangle going simultaneously, right? So if you want to draw the entire frame buffer, we specify a scissor rectangle that's covered it entirely. Okay. VK rect 2D scissor equals, oh, it's just scissor dot offset equals 0, 0, and then scissor dot extent equals, it's the swap chain extent we have. Cool. So there's a scissor. So the scissor vectors can be specified using a static part or a dynamic state set in the command buffer, while the former is more in line with other states if it's often conventional to make viewport. It's often conventional to make them dynamic. It has flexibility. This is very common, and all implementations can handle dynamic state without a performance penalty. Ah, nice. When opting for dynamic viewport and scissor rectangles, you need to enable the respective dynamic states for the pipeline. Ah, and that's what we did before. We created them as dynamic states. This makes sense. And you only need to specify the count at pipeline creation time. And they will be set up later during draw time. Sorry, what are we doing? Viewport creation. VK pipeline viewport state create info. Let me just say there's one. Okay, sure. Wait, what are we doing? Draw to it, and so that's where the dynamic state comes from. Oh, that just automatically creates it, so I didn't have to do any work here. Okay, so that's effectively what I did was equivalent to that. Sure. And so without dynamic state, the viewports need to be set in the pipeline using this. This makes the viewport and scissor doing stuff. Independent of how you set them, it's possible to use multiple viewports and scissor rectangles on some graphics cards. So the structure members with reference an array of them. Using multiple requires enabling a GPU feature. See logical device creation. Okay, cool. I will be deleting those. Amazing. Rasterizer. The rasterizer takes a geometry that is shaped by the vertices from the vertex shader and turns it into fragments that to be colored by the fragment shader. It also performs depth testing, face coloring, and the scissor test, and it can be configured to output fragments that fill entire polygons or just the edges. This is configured using the VK pipeline rasterization state create info. I'm going to reveal I'm tired of manually typing out all of these state creation infos. They're annoying. They're really annoying, you know? But yeah. If depth clamp enable is set to VK true, then fragments that are beyond the near and far planes are clamped to them as opposed to discarding them. This is useful in some special cases like shadow maps. Doing this requires enabling a GPU feature. So rasterization, rasterizer dot rasterize, whatever. We're disabling it. We're disabling we're not enabling the discard. If rasterizer discard enable is set to VK true, then geometry never passes through the rasterizer stage. This basically disables any output to the frame buffer. Okay, whatever. Polygon mode. We're filling the polygons. Yes, this is true. Polygon mode determines how fragments are generated for geometry. The following modes are available: fill, line, and point. So using any mode other than fill requires enabling the GPU feature. Rasterizer.line width. Yes, checks out. Keep lines same width. The thickness of lines in terms of number of fragments. The maximum line width that is supported depends on the hardware. Any line thicker than 1.0 requires you to enable the wide lines GPU feature. There's a bunch of GPU features that you have to enable for Vulkan. Maybe have it as default, but sure. And then for culling, we color mode back bit, and front face we expect to go clockwise. So face culling, color front faces, we color. We color. Rasterizer.depth bias enable false, and then some constant factors that I will keep in, because these creation settings are actually kind of insane. Amazing. So the rasterizer can alter depth values by adding a constant. So, but we are not doing shadow mapping, so set depth bias enable to be false. Did we set it? Depth clamp enable to be false. Okay, sure. Multi-sampling. This multi-sample state configures multi-sampling, which is one of the ways to perform anti-aliasing. So you sample the same pixel multiple times, and then it will do anti-aliasing. So, oh dear God. Sure, we're disabling it at the start. Sure. This is going to be a monster function that takes in all of these. Depth and stencil testing. Oh my God, Vulkan, what are you doing? What are you doing, Vulkan? This is actually insane. Yeah. This is, yeah, no, I'm gonna drink some water at this point, because this is too much. Depth and stencil testing. So if you're using depth stencil bumper, then you configure it. We don't have one, so we can do null pointer, so we don't. Okay, so we don't worry about it. Cool. Color blending. After fragment shaders return a color, it needs to be combined with the color that is already in the frame buffer. This transformation of color blending, there's two ways to do it: mix the old and new, or combine it using a bitwise. The two types of structs to configure color blending. The first struct is blend attachment state, is the configuration per attached frame buffer, and the second struct contains a global color blending settings. We only have one frame buffer, so yoink, because that seems like a lot. Let's read it. So color right mask means we're writing to, oh my God, we're writing to all the colors. We're not doing any blending. We're just not doing any blending. Sure. Amazing. This per frame buffer struct allows you to configure the first way of color blending. The operation that will be performed the best demonstrated using the following pseudocode. If blend enable, then RGB is we do some blending, and the alpha will be blend as well. Otherwise, we just set the final color to be the new color. Okay. So we're not blending it, we just display it. Cool. The most common way to use color blending is into alpha blending, where we want the new color to be blended with the old color based on its opacity. The final color should then be computed as follows. Sure. So new alpha times new color. Okay, so we have a constant blending. So this can be accomplished by doing that. But you can find all of them in the spec. Okay, we check the spec for those details. Cool. Now, the second structure references the array of structures for all the frame buffers and allows you to set the blend constant you can use as blend factors in the aforementioned calculations. Oh my God. Cool. Amazing. Sure. So we just set all the blending. We're just not doing any blending. Pipeline layout. You can use uniform values and shaders which are global, similar to dynamic state values, like when you change at drawing time to alter the behavior of shaders without having to recreate them. They're commonly used to pass a transformation matrix to a vertex shader or to create texture samplers in the fragment shader. Okay. So these uniform values need to be specified during pipeline creation by creating a VK pipeline layout object. Even though we won't be using one until a future chapter, we still require to create an empty pipeline object. Cool. So we create a pipeline layout object and create the object in the... Okay, I will be yoinking that because I am tired of setting all of these like infos and all of that like nonsense. If VK create pipeline layout with a device, VK pipeline create info it's a reference to pipeline layout info. Our allocator is going to be a null pointer, and pipeline layout is going to be a reference to pipeline layout. And if this is not equal to a VK success, then what we do is we throw an error. Throw standard runtime error, and this runtime error is going to be failed to create a pipeline layout. Cool, and it also specifies push constants and the ranges, so it's another way of passing dynamic values that we may get into a future chapter. The pipeline layout object will be referenced throughout the public's lifetime, so it should be destroyed at the end. Okay. Swap chain surface. Where's like cleanup? There's a cleanup. And this should be first. VK destroy pipeline layout. Oh, it's a class member. Okay. Device pipeline layout. And the allocator is going to be a null pointer, as it always is, because we haven't made our own allocator. And then we go back up here. A lot. Oh my god, there we go. Pipeline layout. This is a class object. Here. I'll paste it down here, so there we go. And so there we have it. We have a swap chain, we have a pipeline creation object, and yeah, there we go. Cool. So that's a swap chain function. That's the image views. There we go. Cool. So we've written to it and then we destroy it. And so that's all the fixed function state. It's a lot of work to get this all set up from scratch. But the advantage is now we're nearly fully aware of everything that's going on in the graphics pipeline. This reduces the chance of running into unexpected behavior because the default state is not what you expect. Cool. One more object, and we have to create a render pass. Okay, so I'm probably just going to get the render pass set up, and then from there I'm going to, yeah. I think that's probably going to be the end of today's stream, because this is, woo-wee. And the next stream, we get the first triangle up. So, setup. Before we can finish creating the pipeline, we need to tell Vulkan about frame buffers that will be used while rendering. So we need to specify how many it is. So we need to create a render pass, and so we create it before we create the graphics pipeline. Cool. Before we create the graphics pipeline, we create render pass, and this is going to be a void create render pass, and there we go. And so in our case, we have just a single color buffer attachment represented by one of the images from the swap chain. Oh, okay, sure, that's actually pretty simple. VK attachment description color attachment, and so color attachment dot format is going to be the same as a swap chain format. swap chain image format, our color attachment dot samples is going to be VK sample count 1 bit, VK sample count 1 bit. Cool. So the format of the color attachment should match the format of the swap images, and we're not doing anything with multi-sampling, so we'll stick with one sample. Color attachment dot load up. Color attachment dot load up. That's going to be the clear. Okay. VK attachment load up clear, and then color attachment dot store up is going to be VK attachment store up clear. VK attachment store up, not none. It's going to be store up store. There we go. So they determine what to do with the data and attachment before rendering and after rendering. So load, preserve is the existing contents, clears the value to a constant to start, and then in existing don't care is we don't care. Store up is rendered content will be stored in memory to be read later, and don't care is they'll be undefined after we render them. So we're interested in seeing the render triangle on screen, so we're going to go to store up here, and then stencil load and store. We don't care because we don't have stencils. I'm just going to copy paste at this point. Initial layout will be undefined. Our final layout will be present SCHKHO, which is the image presented in the swap chain. Checks out. Cool. Color attachment is image uses color attachment, and DST is destination for memory copy. Cool. So the initial layout specifies some stuff, and yeah, we keep doing that. Amazing. So from here, subpasses and attachment references. A single render pass can consist of multiple subpasses, and yeah, okay. So the reference is color attachment reference. It's a reference to it that contains some other info, like nothing's actually attached to it yet. We're going to say the layout should be optimal. You know how it is. You know how it is. The subpass is described using a VK subpass description structure. Sure, and it's bind point graphics. Yep. Vulkan may also support compute subpass in the future, so we have to be explicit about it being a graphics subpass. Next, we specify a reference to color attachment. Yep. We have one color attachment. And so this, the index of the attachment of this vector is directly referenced in the fragment shader with the layout location used. Ah! There's one. I see. The following other types of attachment can be referenced by subpass P input attachments. So attachments are read from a shader. Attachments are used for multi-sampling, stencils, and preserve. Okay. Render pass. Now that the attachment and the basic subpass references have been described, we can create the render pass itself. Create a new class member to hold the VK render pass right above the pipeline layout variable. Okay. Now we have to create the render pass. Well, oh no, it's below this. Yep. This is going to be a VK render pass. That's a render pass. Is it going to be above this? Yep. Now, if we go back to create render pass function, we actually create the render pass at this point. It's above here. Oh my god. Insane functions. VK render pass create info render pass info. I'm going to be yoinking these because hold on, I misinputted. There we go. I'm yoinking those because that's how it is. And there we go. We have all the stuff from our render pass, and we just do an if VK create render pass. Amazing. Amazing. Just like the pipeline layout, the render pass will be referenced throughout the program, so it will only be cleaned up at the end. Oh boy. Where is... Look, clean up. There we go. After destroy pipeline, yep. There we go. This may seem like a lot of work, but in the next chapter it all comes together to finally create the graphics pipeline object. Dear God. Okay, I think I'm going to be stopping my stream here because that was a lot. And I'm tired and my voice is tired. So I will be seeing you guys all later. Goodbye.